Sometimes we have a problem where it's ambiguous which direction the reaction goes to come to equilibrium. So let's solve the following problem to see if we can see what we can do to solve a problem like this. So we're charging a vessel with sulfur dioxide, oxygen, and sulfur trioxide. So we're putting some of everything into our vessel. And then we allow this reaction to come to equilibrium, and we want to know what the total pressure is. We have an equilibrium constant that goes with this reaction. So let's just charge ahead and solve this problem like we always would. So we're going to write the reaction that is coming to equilibrium. And we are going to enter our initial amounts. So we're told that we have 0.1 bar of the SO2, we have 0.2 bar of the oxygen, and we have 1 bar of the sulfur trioxide. We can see that the equilibrium constant is large, and so we would expect to have mostly products. And in fact, we do have mostly products, but the question is, are we at equilibrium? Are we, do we need to go in the forward direction to get to equilibrium? Do we need to go in the backward direction to get to equilibrium? And we don't really know. And so the best way to figure that out is to calculate Q. So Q is, remember, the reaction quotient when we're not at equilibrium. And so at these initial conditions, we suspect that we're not at equilibrium. And so to calculate a Q, we need the concentration or the pressure of SO3 squared divided by the pressure of oxygen divided by the pressure of SO2 squared. And so my Q value is going to be 1 squared divided by 0.1 squared divided by 0.2. And if I put that into my calculator, I'll find that this is equal to 5 times 10 to the 5th, which is a large number, but it's clearly smaller than my K. And so this is smaller than K. That means that I need to do something that will increase this value. And to increase this value, I need to increase the numerator and decrease the denominator. That means I need to make more products and lose reactants. And so I know that my reaction is going to go in this direction to get to equilibrium. So to get to equilibrium, I'm going to need to change these concentrations by making 2x of my sulfur trioxide, losing x of my oxygen, and losing 2x of my sulfur dioxide. Now, before I get too much further, let's think a little bit about down the road whether we're going to be able to make an approximation or not. And so we have a very large equilibrium constant, so we suspect that we should be able to make an approximation. But we need to think carefully about whether the way in which we've set this problem up right now means that x is small or whether it means that x is large. 5 times 10 to the 5th is way, way, way smaller than 4 times 10 to the 24th. So I'm a really long ways away from equilibrium, meaning that I have to change my concentrations by a lot in order to get to equilibrium. That means that x, in this case, is going to be pretty large. So it would behoove me to actually do the limiting reagent problem and to start my equilibrium all the way over at products, because I have a large value of K, and so I know I'm going to end up with almost all products and very, very few reactants at equilibrium. So I know I'm going to proceed to make products, and so I need to know which of my reactants is the limiting reagent. In this case, I can kind of tell by inspection because I need twice as many sulfur dioxides as I do oxygens, and I have less sulfur dioxide than oxygen. So sulfur dioxide is going to be my limiting reagent, which means I'm going to use up all of my sulfur dioxide. And so I'm going to end up with 0.1 minus 2x is equal to 0 because I use up all of my limiting reagent. That means that 2x is equal to 0.1 and x is equal to 0.05. And so if I use up 0.05 of the oxygen, I'm going to be left with 0.15 of my oxygen. And if I make 2x of the sulfur trioxide, I'm going to end up with 1.1 bar of my sulfur trioxide. So my new initial conditions are going to be that I have 0 of the sulfur dioxide, and I have 0.15 of the oxygen and 1.1 of the sulfur trioxide. Now I can see that I'm not at equilibrium because I don't have any of the sulfur dioxide. And so now to get to equilibrium, I actually need to go back a little bit towards reactants, and I need to make 2x of the sulfur dioxide, make x of the oxygen, and lose 2x of the sulfur trioxide. Now, if we've done this correctly, x should be small, and that means that I can ignore x relative to any initial concentrations that I have. So I should be able to ignore x relative to 0.15 and ignore 2x relative to 1.1. And so I should be able to write that at equilibrium I have 2x of the sulfur dioxide, I have approximately 0.15 of the oxygen, and approximately 1.1 of the sulfur trioxide. And so I know that my equilibrium constant expression is the concentration of sulfur trioxide squared. And so I'm going to have 1.1 squared divided by the concentration of oxygen, or the pressure of oxygen, divided by the pressure of SO2 quantity squared. So I'm going to have in the denominator 0.15 and 2x quantity squared. And that's going to be equal to my equilibrium constant, because this is going to, I want to solve for what my equilibrium concentrations are. And so now I should be able to just solve for x in this equation and find out the pressure of sulfur dioxide. And once I know the pressure of sulfur dioxide, which will be 2 times x, I can add up all of these pressures to get my total pressure. So to solve this problem, I'm going to divide both sides by 4 times 10 to the 24th and multiply both sides by 2x quantity squared. And that's going to give me 1.1 squared divided by 0.15 divided by 4 times 10 to the 24th is equal to 2 squared is 4x squared, so I have 4x squared. And so let's just plug all of this mess into our calculator, and we get 2 times 10 to the minus 24, and that's going to be equal to 4x squared. And so if I divide both sides by 4, I'm going to get that x squared is equal to 0.5 times 10 to the minus 24. And then I have to take the square root of both sides, and so x will equal 7.1 times 10 to the minus 13 bar. And we can see that our assumption that x was small compared to 0.15 and 1.1 is definitely true. And so now we can calculate the total pressure. So the total pressure is going to be the sum of all of these equilibrium pressures. And it won't really matter whether we add 2 times 7.1 times 10 to the minus 3 to these two pressures, because it's not going to change the answer. And so our total pressure will be 1.6 bar at the equilibrium point.